We'll now talk about some problems in algorithms where things get, how do I put this, a little out of control. So far, we've talked about algorithms that are theta of log n, theta of n, and theta of n squared time. And remember that the order of magnitude determines how quickly the values grow as n increases. So here, we've talked about algorithms where the total amount of work done is no worse than a constant multiple of n squared. So, an algorithm of order log n does less work as n increases than does an algorithm of order n, and that does less work than one of order n squared. So these are pretty good, and order of n squared is still a polynomial of n. So we say that these algorithms are polynomially bounded with respect to n. So what we're saying here is that if n is the size of our input, the running time of these algorithms, or the order of magnitude of these algorithms, is at most a polynomial of n. But the thing is, this isn't always going to be the case. There are going to be some algorithms that has to do work that is not polynomially bounded. Let's take a look at an example of a problem where we will find that the amount of work is more than polynomial bounded. So let's say we have 4 different cities, A, B, C, and D, laid out like this, where we have the cities connected in a square fashion. So the question we want to ask is it possible to start at city A and we'll go through all the other cities exactly once, no more and no less, and then we end up back at A? And if we take a look at this, well, let me ask you, pause this video for a second and see if you can find some possible paths from A, visiting all the other cities, and then ending back at A, and then resume the video once you have your answers. So if we take a look at this, we find that there are 2 possible paths. So we can go A, B, D, C, and then back to A. We can also do A, C, D, B, and then back to A. Now, that works fine for us, but remember, we have to think of this in terms of a computer. A computer cannot see this graph, well, we call this a graph technically, but we see these cities in front of it and then make this distinction. So we have to tell a computer how to traverse these paths to find all the cities and then getting back to A. And this problem is what we call the Hamilton circuit problem. If we want to have a computer solve this problem, we have to look at every possible path from a city to itself. There really isn't a more efficient way just yet. So if we're going to do this, we have to ask ourselves, how many possible paths are there? Well, every time we move from one city to another, we have 2 choices to make. We can either go to the next city or we can go backwards. Now you might think, well, it would make sense just to keep going forwards and never go backwards, but it is a possible path that we have to consider. So for example, let's say we start at city A. We can then go to either B or C. If we pick B, then we can go either back to A or we can go to D. Well, let's say we go to D. If we go D, then we can go either to B, or we can go back to B, or we can go forward and go to C. Let's now consider the total number of options at each step. So every time we take one step towards a city, the grand total number of possible options that we've had actually doubles. And you might think, wait, what do you mean by that? Let me give you an example. So let's say we start at A. Within 2 steps, we have 4 possible paths. Remember, we said earlier that if we start at A, we can either go B or C, so that we have 2 options within 1 step. Now, within 2 steps, we have 4 possible paths that we can travel. We can either do A to B, then back to A. We would have A to B to D. We would have A to C, then back to A. Or we would have A, C, and then D. So these are the 4 possible paths within 2 steps. Now, what about within 3 steps? Well, we would have 8 possible paths. I'm not going to list all 8. You can try that out on your own to see the 8 possible paths that we would get if we were to go 3 steps starting from A. And if we had 4 steps, so within 4 steps, we would have 16 total possible paths. So what we're seeing here is that every time we take a step, the total number of possible paths doubles for us.